Okay, so today I'd like to talk a little bit about continuity at a point. So we're going to start off with some function, let's call it f, and we're going to look at what happens to that function at a specific x value. Let's fix that x value at c. All right, and we're going to talk about continuity. Obviously, there is a discontinuity in this graph. There is a break in it right here, right? It's actually a jump, right? And we're going to see what more rigorous explanation of why this is. This kind of discontinuity is called a non-removable discontinuity. And I will show you why. All right, so here is the definition of continuity at a point. For a function f to be continuous at point c, comma, f of c, then three things have to be true. First of all, the f of c has to be defined. Let's take a look up here. If you look at the x value c, the x value c does relate to a specific y value. If x is c, then y is equal to a, because there's where the point is, you see? There's an ordered pair c comma a that would satisfy this function, that would when you plug in C, you would get A as the return. So the f of C is defined, and the f of C is actually defined to be A. So the first criteria is met. The first criteria is met. The f of C is equal to A. So it's defined and equal to A. The next thing we want to do is we want to check the second criteria. The second criteria says that the limit as x approaches c of the f of x exists. Well, let's see. If I'm approaching c from the left-hand side along the function f, it would seem to me as the y values are approaching a. If I'm approaching c from the right-hand side of f of x, if I'm approaching c from the right-hand side this way, it would seem as though my y values are approaching b. So the limit as x approaches c of f of x does not exist. So here's what we have. We have that the f of c is equal to a. So the first criteria is met. But now we find that the limit as x approaches c of f of x does not exist. Does not exist. So since the limit does not exist, the third criteria is impossible. You see, the third criteria says that the f of c, which would be a, would equal the limit as x approaches c of f of x. That doesn't exist. Because this doesn't exist, it cannot possibly equal a. So therefore, this is also not satisfied. Anytime 1 or 2 is not satisfied, automatically 3 will not be satisfied. Okay? In the case here of a non-removable discontinuity, the reason why the limit doesn't exist is because of number 2. The reason why the function is not continuous at c, so the reason why the function is not continuous at c is because the limit as x approaches c does not exist. So anytime the case is that the second criteria is not met or the limit does not exist, we will get a non-removable discontinuity like this one, all right? Here's another non-removable discontinuity. Okay, so we have the function f, we have the value c. Notice there's a vertical asymptote at x equals c. All right. So if you're going to check through these things here, the f of c is not defined. If you plug c into this function, you won't get a value back. It's actually undefined. In this case, the f of c is undefined. It's a vertical asymptote. And then when you check the next criteria, the limit as x approaches c of f of x, this one does not exist. You see, if you take a look, as you approach c from the left-hand side, y just keeps climbing and climbing and climbing and getting higher and higher, larger and larger. So as x approaches c from the left, y increases without bound. As x approaches c from the right, once again, y increases without bound. Therefore, the limit as x approaches c of f of x is not a fixed number, so it does not exist. So now, in this case, not only is the f of c not defined, but also undefined actually. Not only is the f of c undefined, but also the limit as x approaches c of f of x does not exist. Whenever the limit does not exist, you have the case where it is a non-removable discontinuity. And because this one is not defined and this one does not exist, 3 is impossible. We don't even have to check 3 because neither one of these things is exists. This is undefined and this does not exist. All right, let's take a look at the case now of a removable discontinuity. So you notice here that this kind of discontinuity could be plugged in. If I just define the f of c as a, that hole in the graph would be plugged in and I would have removed the discontinuity. So this is what we call a removable discontinuity. If you check the criteria here, the first one, the f of c is defined. Well, there is no f of c. There's no point vertically above or below c for the function f of x. So when x is equal to c, there is no value. So the f of c is not defined. F of c is not defined. But the limit as x approaches c of f of x here, well, as you approach c from the left side, it seems like y is approaching a. As you approach c from the right side, y also seems to be approaching a. So it turns out that the limit as x approaches c of f of x is equal to a. And once again, because the first criteria is not met, it's impossible for the third criteria to be met because the f of c is not defined. It cannot equal a. So the third criteria are also not met here. But the reason why the third criteria is not met is different in this case. In the first two cases, the cases of the non-removable discontinuity, the limit did not exist. In this case, the limit does exist, but the function is not defined. The function is not defined at that value of x, at c. Okay? So for a removable discontinuity, the limit, the second criteria will be met. The limit as x approaches c of f of x will exist. Okay? So this one is a removable discontinuity. Removable discontinuity. Let's take a look at one other case here. Here's another case. The only difference here is I've actually defined the f of c to equal b. The f of c is equal to b here, okay? So let's check our criteria. First criteria. First criteria is the f of c is defined. That's true in this case. The f of c in this case is actually equal to b. The f of c is equal to b. The second criteria is the limit as x approaches c of f of x exists. From the left and from the right, as you approach c on the x-axis, y seems to be approaching a. So the limit as x approaches c of f of x is equal to a. Because the second criteria is met, because the limit exists, it means that this discontinuity is going to be removable because the limit exists, okay? The third criteria now, this is the first time we've actually checked the third criteria, and it's because the first two criteria checked out. The first two criteria have been met, so we have to check the third one. The third one says the f of c, which is equal to b, equals the limit as x approaches c of f of x, which is equal to a. Well, that's not true. Those two do not equal each other. So even though there is a functional value and the limit does exist, because those two are not the same, we have a discontinuity. And all we have to do is define or redefine actually the f of c to be a, take it away from here and plug this hole, and we would have removed the discontinuity. So this is another case of a removable discontinuity. Let's take a look at an example here. All right. It says identify all values of x for which this function is not continuous. Specify whether the discontinuities are removable or non-removable. Okay, well, there are only really two values of x that we really have to take into consideration. We'll see that if we factor everything. So we're going to factor, this is already prime, so we only have to factor the denominator. When we factor the denominator, I see that this is x minus 1 times x plus 2 when I factor it. All right? So what I want to do is I want to check all the criteria. Okay? Well, there's a point, or there's an x value, two x values actually, that if I plug them in, weird things happen, right? If I plug in -1, I'll get division by 0 here. And if I plug in, or not -1 actually, sorry. If I plug in positive 1, I'll get division by 0 here. And if I plug in -1, I'll get division by 0 also. So these are the two x values that I have to concern myself with. All right? X equals 1 and x equals -2. So let's check all our criteria for both of those. Let's start with x equals 1. X equals 1. The first thing I want to check is that the f of 1 is defined. Well, let's see. The f of 1 would equal uh, 1 minus 1 divided by 1 minus 1 times 1 minus or plus 2. And in this case, I would get 0 on top over 0 on the bottom. 0 over 0. 0 over 0, okay? So I realize that the f of 1 is not defined. So automatically, I know that this thing is not continuous at x equals 1. I just want to check to see what kind of discontinuity it is. So I'm going to check the second one, the limit as x approaches 1 of 1 minus 1 over 1 minus 1 times 1 plus 2. Well, obviously, when I do direct substitution, I get 0 over 0. So I have to, oops, well, these would be x's, my fault. Copied the wrong thing. I should copy the function. Okay, obviously if I directly substitute 1 in, this is 1 minus 1, 1 minus 1, and then 1 plus 2, I get 0 over 0 the same way I did here. So what I want to do actually is I want to cancel out that common factor, the limit as x approaches 1 of 1 over x plus 2. So I actually do get a limit here because I cancel that factor. And the limit is equal to 1/3. So I find out that the limit as x approaches 1 of x minus 1 over x minus 1 times x plus 2 is equal to 1/3. Since it's equal to 1/3, I know that this discontinuity is removable. Because removable discontinuities are the ones that give us limits. Okay, we don't have to check the third criteria. We already know it's not continuous. We were just checking the limit to see if it was removable or non-removable. All right. All right. So let's check the other one now. Let's check x equals -2 now. So for x equal -2. Well, in this case, the first thing we want to do is we want to check the f of -2. The f of -2. Well, the f of -2 is equal to, is going to be -2 minus 1 over -2 minus 1 times -2 plus 2. So I get here -3 over 0, which is undefined. So I also have a discontinuity at x equals -2. If I want to know if it's a removable or non-removable discontinuity, all I have to do is check the second criteria, the limit as x approaches -2 of x minus 1 over x minus 1 times x plus 2. Well, direct substitution still gives me undefined, um, because once again I have -3 over 0 on direct substitution, so this is undefined again. So therefore, since the limit does not exist, I know when the limit doesn't exist, I have a non-removable discontinuity. So the first example, when x was equal to 1, when x equals 1, that is a removable discontinuity. It's just a hole in the graph. I could plug that hole by defining the f of 1 to be 1/3. If I define the f of 1 as 1/3, I will have removed that discontinuity. The second one is non-removable. That one is actually a vertical asymptote. All right, so that's the distinction between removable and non-removable discontinuities.